Hello everyone. Right now I'm working on a simple project of CCUS. I want to convert a gas producer to be CO2 injection well. And this is the model for the production well. Okay, you see the fluid, dry and wet gas, and then the method, black oil. Okay, separator, single stage separator. Okay, PVT warning, no, disable warning. Okay, water viscosity, water vapor, no calculations, flow type, tubing flow, well type producer, method none. Okay, and yeah, maybe we can type in the model convert from gas producer to CO2 injector. Okay, this is actually the original model, and then this is on land, on shore, rough approximation, range full system. Okay, sol, none. Okay. Later, we will convert this well from producer to injector, and then we will inject CO2. For CO2, we must use equation of state, and CO2 will undergo phase changes, liquid to gas. So we will use retrograde condensate, but for now, we will just check the original model. Click OK or done. Now we can check the tutorial, maybe contents. We can check here tutorial for CO2 injection in Prosper. Okay, problem statement is part of study into storage of CO2 is to build for injector well, which can estimate the pressure drop down the well and also model the inflow into the reservoir. It is assumed that the reservoir fluid is CO2. Okay. However, when this is the case, it is normally best to model the IPR aspect of the model using numerical simulator. Okay, of course. Numerical simulators should certainly be consulted when injecting CO2 into depleted hydrocarbons reservoirs, as the immiscibility of the injected fluid with the reservoir fluid and the impact of temperature on the fluid may have a large impact on the movement of through the reservoir. Okay, so basically we need to use numerical simulator, of course, in order to capture the phase changes and fluid properties of the carbon dioxide at different pressure and temperature within the well. Fully compositional equation of state. Okay, we will use EOS, equation of state, has been created in PVTP, and this should be used to describe the PVT properties. Okay, as it is possible that the fluid may be a liquid or gas within different segments of the well, depending upon pressure and temperature. It is important that the retrograde condensate fluid option is selected. Okay, so we will select equation of state and retrograde condensate. Once the model has been built, an estimate of injection rate when the wellhead pressure is 2500 psig is required. Okay, so this will be the wellhead injection pressure. All right, and then the objective. The objective of the tutorial are to create a preliminary retrograde well, to which more information. Okay, import an equation of state, learn the basic input, perform a system calculation. Okay. Okay, I think it's the basic fluid, retrograde condensate, equation of state, internal equation of state model, well type injector, PVT. Okay, so we will use Peng Robinson. Later, correct CO2 density, yes. Water salinity in this example, 20,000. Path to surface, flash straight to stock tank. Okay, flash straight to stock tank. Lawrence Bray Clark. Okay. Okay, so this is just the case, deviation survey, downhole equipment, nothing special. So tubing, safety valve if we use that. But in this case, we don't install subsurface safety valve, tubing and casing, of course. And then geothermal gradient. The geothermal gradient is temperature gradient of surrounding rock. Okay, so nothing special. IPR data. So because we will inject into gas reservoir, so I think the GOR is template 1000 SCF per STB, and assuming no gas and no water, so water gas ratio 0. Okay, and this is the analytical IPR model using petroleum experts inflow model. Okay, we will use our empirical method in my case, and steps by step guide. Okay. Okay, so this is maybe very important. Setting up the model. Okay, we can read it. A new file should be open. If Prosper has just been opened, new file has. Okay, the first step in any Prosper model is to set up the type of well. Okay, so we'll use retrograde condensate, equation of state, well type to injector here, retrograde, equation of state. Okay, injector, improve approximation. Okay, so let's be careful here. Improve approximation. To set up the equation of state, select EOS setup, Peng Robinson, correct CO2 density. Okay, flash straight to stock tank. This screen is used to select the EOS model to be used, as well as setting the path the fluid will take to surface and other options. Okay, the equation of state which was used during characterization process was the Peng Robinson, and therefore this should be selected at the top of the screen. If required, it is possible to model the viscosity of fluid using other methods such as black oil correlations. Here, okay. New to IPM version 8, Prosper version 12 is the ability to model the CO2 properties using correct CO2 density option. Okay, good. This will apply a volume shift to the EOS selected so that the density calculated for CO2 fluid match those with which come from the field. Okay, and also uses new enthalpy values to ensure that the heat capacities, etc., of the fluid are captured accurately. Okay, so correct CO2 density is very important. This new method has been shown to recreate the values obtained using the Span-Wagner EOS, but it is also able to handle CO2 streams with high percentage of other impurities. Okay, at the bottom of the screen, the path which the fluid takes to surface can be entered. As we are using an equation of state model, the composition will be flashed to standard conditions to find the equivalent stock tank. Okay, a certain fluid properties such as GOR, gravity, or gravity are dependent upon the path taken. It is important to enter a path to surface which is representative of the actual field values. In this case, the values will be obtained by flashing the fluid straight to stock tank and not passing through any separator drains. Okay, which one? Use path to surface so object. Okay. When this section has been completed, select OK and then return to main Prosper when calculating CO2 properties. But our case is modeling a fully compositional CO2 well. Okay. Okay, yeah, it's the injector, right? When calculating CO2 properties, relatively small changes in the pressure and temperature can cause a large change in the fluid properties, as the phase can change, of course. In order to capture these sudden changes in the fluid properties, the step length can be reduced. Okay, this will increase the time it takes to carry out the calculation. However, it should allow the calculation to be more accurate. This can be done by okay limits So later on, calculation step length 50 feet. Use correlation step length, yes. Okay. At the bottom, calculation 50 feet. In order of the for the use correlation step length, yes. Okay. PVT. Okay, as PVT previously been created, which is representative of our reservoir fluid. This is called, okay, and can be found. Okay, so in this case, in this prosper case, CO2 89%. But in my case, I will inject 100% CO2. Reservoir temperature, okay. And then specifying equipment, nothing special here. Deviation survey, surface equipment, no. We don't simulate that. Donal equipment, yes. Geothermal, catch detail, imputing IPR. Okay. IPR curve pressure, IPR temperature, okay. Because we simulate an injector, the IPR will be like that. Okay, positive gradient. Okay, will be like this instead of this. Okay. Okay, and then this is to run the VLP also, IPR VLP. Okay. And then inserting calculation. So calculate. All right, the right method, running a system. It can be seen from this, if the well pressure and WGR, the model that the well will flow at approximately 28.9 corresponding to, okay, gas rate. Okay. Yeah, IPR will be the red line and then VLP will be like this. Okay, so we will follow this example. Okay. All right. Okay, so now we will check the PVT. Basic, okay. The PVT is basic using black oil, gas gravity, and then condensate gas ratio, condensate gravity, water gas ratio. Okay, so we have 8.7, yeah. Water salinity 12,000. Gas viscosity. Okay, they don't have laboratory data. Done. Okay, water salinity 12,000. Okay, no H2S, no CO2, no nitrogen. 8.7, okay, cancel or done. Okay, so this is very important. Reservoir pressure 750, reservoir temperature 212. Okay, we have this one, water gas ratio, condensate gas ratio. Okay, and then this one, CNN method. Okay, and we check, we have well test data. At this date, the comment flowing bottom hole pressure, the gas rate at the measurement date, and the flowing bottom hole pressure 603. Okay, and then if we calculate, so we can get absolute open flow of 11, okay, 11 mmscf per day. If you plot the pressure and, yeah, the pressure, click done. Okay. So the well test data here, okay, it's acceptable. Okay. How much we will inject, we will check later. Finish. Okay, done. Click done. Okay, and then this is the well. Double click. Check this one. Tick this one. Edit. Okay, so it's a vertical well. Good news for us. 0 to 4500. Click done. So we have Christmas tree, tubing, okay, and then casing inside diameter 4.95. Okay, it's easy. So this is the geothermal gradient. Okay, so the plot. All right, finish. Click done. Okay, typical value. Click done. So if we do calculation IPR VLP, currently the wellhead pressure is 374, water gas ratio 8.7, condensate gas ratio. So they simulate with Bex and Brill. Okay. Okay. So the rate is 3.7 mmSCF per day. Okay, non-sensitivity they use. Okay, like this one. Okay. And this is the well test data. Okay, click done. Did they do other operation? Gradient? Okay, no. Blank. VLP. Okay. Yeah, we can also create the VLP if we press calculate. Okay. Oh, they create so many cases. I want to cancel first. Yes. Check the cases. Oh, they do many cases. Top knot pressure, condensate gas ratio. Okay. So I will just check the result then. Plot all cases. Oh, okay. So we have so many cases. Yeah, usually we use this, we create many cases so that the cases can be uploaded to MBAL or pros or gap. Okay, so I think it's already comprehensive. Choke, generate for gap, behave BHP from wellhead, no, later. Okay, so I think it's already good. The model can be used. Now I will copy this file. And then I will turn this production well model to injection well model. Okay, so I will pause for a while. Okay, now let's do this. Fluid I will change to retrograde condensate, and then method I will change to equation of state. Equation of state we will use Prosper internal EOS model, separator multi-stage. Okay, no PVT warning. Water viscosity we can use correlation. Water vapor no calculation. Okay, flow type tubing flow, well type injector. And then it is onshore. The model we will use improve approximation, full system, brine properties default, case hole, send control none, single branch. Okay, click done. All right. Now, double click here. This is the window for equation of state, compositional model. Okay, so viscosity model, we can use as per the example. We will maintain this one, Lorentz and Bray-Clark. Also for the viscosity for gas, and then calculation type calculated from EOS model, reservoir temperature 212, salinity 12,000. Okay, it's good. Options, okay, enhanced oil, not enhanced oil, equation of state model Peng Robinson, optimization model can be medium, but high is okay. Correct CO2 density, make sure you select yes, full composition yes, optimize repeat calculation yes, lumping no need for now, reference temperature 60, reference pressure 0, flash mode okay, hydrate, yeah, we can use this one, phase detection method critical point, this also flash straight to stock tank. I think it's okay. Click OK. All right. Now you can see here we have done cancel generate. No composition has been entered. Please enter the components information before entering. Okay. Phase envelope later. Help. Save. Export. Export import fill in table. No. Reset component. Properties. No composition has been entered. Target GOR. Target H2O. Recall report. Okay. So now, because I will inject pure CO2, I will insert the properties for CO2 100% here. I've prepared that. Okay. Okay, here. Copy from my spreadsheet and paste it here. CO2 100% critical temperature this one, critical pressure this one, critical volume, eccentric factor. Okay. Molecular weight. Okay. C is 12. O2 is 16 times 2, 32 plus 12, 44. Okay. Specific gravity. Okay. Bubble point, volume shift, omega A, omega B, paracore, Costal volume, and then Costal AF. It's okay. Okay, it's good. So if you also model CO2, you can use this one, or you can also double check. Now we will generate phase envelope. Okay, again, click this one, phase envelope. Now, this is the result for phase envelope. You can copy this result and then paste on your spreadsheet. Okay, and then critical point, Crickondon term, Crickondon bar, pressure step, integration, minimum pressure, maximum interval, I think. Okay, maximum pressure, minimum step, calculation type, calculation from EOS, equation of state, recalculate if you want, calculate hydrate. I don't think it's necessary for now because if you press this one, you will generate the plot for hydrate along with the phase envelope, and it kind of it is quite distracting for me. So I will not generate. But if you click this one, you will have the result for hydrate here. Show profile points, yes. View profile, plot. Okay, so this is the result equation of state for the CO2. It will not be like dome because it's a pure component. So it will be just like line like this one. But if you have mixtures of component, you will have face envelope that is quite similar with a dome. Okay, it's a pure CO2, so it will be like this. Okay, so yeah, this is the critical point. Click on the term, click on the bar, and critical point. So here we will have supercritical condition. Okay, so here we will have supercritical condition. Actually, I want to, yeah, I expect more in the visualization so that we can know whether in which area we can see solid phase, liquid phase, gaseous phase, and supercritical. But I'm sure here in this zone, we will have supercritical. And it is recommended that CO2 for CCUS, for CO2 storage, the CO2 is injected in supercritical form, okay? So that we can store huge amount of mass, okay, with small volume, okay? Because it's dense phase, okay? You can store CO2 at high amount, huge mass, but the volume will not be that significant, okay? But if it is gaseous phase, then the volume will be, yeah, enormous. Okay, so all right. So we need to be sure that along the wellbore from wellhead through the bottom hole pressure, we can exceed this condition, this critical point condition. So we can maintain the liquid form or supercritical form. Okay, so that's the game plane. The wellhead injection pressure should exceed this one, and across the tubing, okay, across the well from wellhead down to the bottom hole. And when it enters the reservoir, we should expect that CO2 that will be existing in supercritical form. Okay, so okay, we can click from here, we can exit. We can click OK, click done. Okay, I'm just going to save. Yes. Now we check the IPR. Okay, because this is the IPR. This is the IPR for the condition where the well is still a producer. So I want to maintain this productivity. Okay, I want to maintain this productivity because I expect that the injectivity will be more or less similar with the productivity. Okay, again, originally this well is a gas producer, and as a producer it has productivity, right? And then I want to turn it to be CO2 injector, and now it doesn't have it. It no longer has productivity, but it will have injectivity. But my first assumption is that the productivity will be the same with injectivity. So I will maintain this CNN, okay? And I will maintain this total GOR. I will maintain this water gas ratio. Okay, maintain the reservoir temperature, reservoir pressure also I will maintain. But of course, along with the injection time, the reservoir pressure will increase. Okay, but I will just predict the condition, the injectivity when it is first injected. Okay, so let's calculate. Target GOR failed, flash target GOR has failed. Okay, it's okay because actually GOR is not important for now. Now the AOF is 2,991 mmSCF per day. If you plot results, it will be like this. Okay. Yeah, practically, if you inject with high pressure, okay, if you inject at high pressure, you can achieve high rate. Okay. By the way, click finish, click done. Let me check the tutorial, modeling CO2, modeling, yeah, this one. I want to check the IPR. Okay. Yeah, this case also gives very high AOF, right? So if you inject this much, you can get this much. Okay. The pressure, oh, it's big. Okay. Okay, I think we can keep it for now. Okay, we can take it for now. So maybe at bottom hole condition, we can achieve, let's say, to make sure that we have supercritical, let's say if the bottom hole pressure is, let's say, 2200, we can achieve more than 50 mmscf per day. But of course, if we inject at supercritical condition, then we should not use mmscf per day, but it's better if we use ton per day. Okay, like that. Okay, ton per day instead of this volumetric rate. Okay, and also mmscf per day is more relevant for gas. It's not for supercritical fluid. Okay, so we should multiply this one with the density of the CO2. Okay, click finish, click done, click done. Okay, and of course we will maintain the wellbore equipment. The deviation survey will not change. Downhole equipment temperature, the geothermal profile, right, will not change. In, oh, this one is very important. Click done. Heat transfer coefficient. Wait. Injected fluid temperature. It is very important. Okay, 0 Celsius or 20 Celsius. It is, I should ask this with my surface facility engineer colleague, okay? But let's say if in my current scenario, let me check. Okay, so if I inject at, it's not 0 Celsius, it's too cold. If 0 Celsius, yeah, let's say when injected after the CO2 is pressurized, there will be, I'm not sure, but yeah, let's say just convert. Okay, from Celsius, where are you? Celsius, degree Celsius, it's C, 2 degree Fahrenheit. Okay, it's 32, but if it is 20 degrees Celsius, It is 68. Okay, let me try with 68. Okay, click done. Heat transfer coefficient. Oh, it's very, very important. Heat transfer coefficient. Donor equipment or temperature data. Click edit. I should provide the heat transfer. Click, yeah, sorry, I will just check the tutorial first. Click done. I know, click done and cancel. Let me check the case. Yeah, sorry, again, it's not a tutorial per se. It's actually, if you want, you can learn with me. Okay, step by step. Equipment overall geothermal 5. Okay, so 5 is okay. Let's, I will use that for now. Temperature 5. Okay, click done. And then this is 68. Click done. Don't forget to save. Okay, so my main target is actually gradient because I want to get the pressure profile from wellhead to bottom hole. But let me check for this one. Okay, this will be injector nodal analysis. So if I inject at pressure of 1200, okay, and then yeah, I maintain the backsand drill, calculate. Okay, what is this? Error case 1, invalid pressure. Click done first. Okay, there is no case. Okay, cancel. So it's like this. Again, red line is IPR, blue line is VLP. But the VLP is quite difficult to calculate here. But I can get 29 MMSCF per day. Wellhead liquid density 47. IPR, okay, no problem. VLP like this. What is the message again? Invalid fluid pressure. Yeah, I know that it will be difficult to calculate the fluid pressure. Okay. What if we go to gradient? Okay, this will be the main thing. First node pressure, let's say 100, 1200. Inlet fluid temperature 68 degrees. And let's say I want to inject at uh, 10 mmSCF per day. Rate type, total molar rate, hydrocarbon mass flow rate, hydrocarbon molar rate. Let's see if I inject molar rate or mass rate to be in correlation. Let's say I want to use because it's let's say Bex Brill, okay? Because now I expect to inject supercritical fluid, which is more or less a liquid. Calculate. Yeah, the problem will be here. Click done. Yes, so it's quite problematic. What if I change to gas instead? Yeah, the problem will be total GOR. So it's quite difficult to gas rate, let's say calculate, float multiple faults, failed using original. Okay, done. Let's say if I input this one, still problem, right? This is 8 total gas oil ratio. 0. Can we calculate that? Target gas has, okay, let's say if I just want flash target GOR has failed. Okay, let me deal with one first later. Okay. Okay, let me try again. Gradient. If the wellhead injection pressure is 1200, water gas ratio 8.7. 8.7. Okay. Total GOR, let's say just for start at 500, inlet fluid temperature 68, and then gas rate 10. What will I get? This one is Becksen Brill. Okay. Calculate. Okay. Let's just select or Mukherjee Brill. Oh, petroleum experts. Let's say what is the correct total GOR then? Failed. Flash target GOR has failed. So if I pressure will increase. But it's quite, I'm not sure about that. Let's say start from 100, 500, 1000, 5000, 10,000, 50,000, 100,000. Okay. It's quite difficult. Gas oil ratio. GOR what? It's a gas reservoir actually, so the GOR should be very high. So, yeah, the GOR should be very high because it's a gas reservoir in the first place. What if the temperature is 20 degrees Fahrenheit, water gas ratio 8? No. Okay. So what's the difference? Oh, it's because this starting from 20. Let's check. Okay. First inject at this. Oh, to 80 degrees. Now check the gradient. Yeah, this one is the gradient for liquid. 0.29 is pressure gradient for liquid, not for gas. So I think it's already good. Let's click done first and save. But I don't think we can maintain that result. If we go back to gradient, oh yeah, we can maintain. But will anything changes if I just change it to 500, for example? Oh, wow, significant changes. Click done. Pressure reduced. Okay. Target UR. Okay. It's quite scary actually. Okay, the gradient is good. But what will happen if I click combinations? Gas rate, let's say I want to inject 5 or 1, 2.5, 5, 12, 10, 12.5, 15, and 20. Click done. Calculate. Plot. Done. All right. All right. Let's see. Okay. First is this. Oh, I cannot. I don't want to plot the temperature. Okay. Pressure. 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 Okay, not bad lah. Cases. Click done. So what's my cases? 1, 2, 3, 4. This is options. This is for grain size, erosion, liquid loading, pigging. Nothing important for now, nothing relevant. This is just layout. This is if I have test data, cases, reset, variable. So I should use all this one. Okay. I don't want to, yeah, like this one and combinations. So 1, 2.5. So I should have, if I 10, 12.5, and 15 and 20. So I should have 7 cases. Click done. So, okay, I don't know. Calculate. Okay, so let's see. Pre-gas density, the gradient, the main thing is gradient. So layout, what do I want? Bottom hole. I don't want this one. Hide all, and then I just want to show the bottom measured through vertical depth, pressure, temperature, and gradient. Turner velocity, no. Erosion rate later. Liquid density, maybe. Oil, total mass flow rate. All right. Yeah, let's say this one. Pound. Okay, done. Can I change the total mass rate to ton? If I change the units, total mass flow rate. Can I find mass flow rate? Let's change it to ton per day. Ton per day. Click OK. So if we go back, save. If we go back to calculation gradient, so what do we have in ton? It's too big. Ton equivalent, eh? So should I change to kilogram per day instead? Just to check. It's not sure about this one. I don't want to show that. Total mass flow rate. Any other? Injection gas rate, injected gas rate. Click done. No. Gas rate. Liquid level. Click OK lah. Liquid density. The gradient shows it's liquid and it's the density. Temperature, okay. Do we have phase? Hold up a regime. Okay. Okay. It will be difficult if I change it to 68. Let's see. No, not really. So it's still okay. And the gradient still shows liquid. plot. Okay. Okay. I think we can keep it for now. Okay. So the issue for this one, we can maintain this total GOR, pressure, and water gas ratio. So if we go back to IPR VLP, calculate. Okay, it is just at this rate, the pressure is invalid. But if we change it to this one, water rate, liquid rate is actually this one. Okay, I think we can accept it, right? This one, blood pressure. If we maintain the pressure, okay. Okay, VLP liquid rate, no. Oil rate, no. Water rate, liquid rate. I think it's okay. Yeah, I think it's okay. So IPR VLP, you click OK. Gradient, okay. So I think we can call it a day. So I've created the gradient. I think it's quite acceptable. And also the nodal analysis. All right, so that's all. It's just one well from 4 wells. Okay, so I think I can continue tomorrow. Okay, thank God. I think I can finish it. Yeah, see you again tomorrow. Thank you.